So let's say we want to, so again, what we're going to do is we want to be able to prove something. And sometimes, how do you know what kind of proof you should be using? Well, I think a good idea would be to use a proof that you think will be the easiest one. So based upon the type of thing that you're supposed to prove, use the easiest approach. So let's say we're asked to prove the following. Tell me if you can read this well. Can you see this?
Yeah.
Let's say we have a sum of some numbers. So let's say as I goes from 0 to, I'm going to say, n. And we're going to add the term of 2 to the power of I. Okay, so when I is equal to 0, what's the value of the term? When I is equal to 0, it's 2 to the 0 or 1. So we have 1. When I is equal to 1, which means that n goes to 1, we have 0 and 1. So we have 1 plus... You hear this? You hear this echo, right? It's not just me, right? I'm not going crazy, right? It was such an echo, I thought somebody else was saying the same thing as I'm saying. So we would have 1, and then as I goes to 1, it's going to be 2. And if n is equal to 2, then it's going to be 2 times 4, so it's going to be 1 plus 2 plus 4. Let's just do one more. So it's 1 plus 2 plus 4, and finally plus 8. And that would be the value for when n is equal to 8. 8, do I do it right? 8. All right, so now let's see what those values are. So basically, this is just going to equal to 1, right? And this is going to equal to 3, and this is going to equal to 7, and this is going to equal to 7 plus 8, which is 15. So it looks like, if you look at these numbers, they are not the most famous numbers you've ever seen, but if you added 1 to them, you'd get 2, 4, 8, 16, and then I guess next is 32, 60. They're powers of 2. But they're powers of 2 minus 1. So if you were to look at this value of 1, you could write this as this is equal to 2 minus 1. And this would be, and now you could, and 2 is also 2 to the first power. So you say 2 to the first power minus 1, and this could be equal to 2 to the second power, which is 4 minus 1, and this would be 2 to the third power minus 1, 2 to the fourth power minus 1. Now in this case, in the first case, the value of n is equal to what? The value of n is equal to what? Is equal to 0. 0. So when n is equal to 0, our summation goes from 0 to 0. Remember, the number of terms in a summation is going to be upper index minus lower index plus 1. So 0 minus 0 plus 1 is 1. So you get one term, and here's that term. When n is equal to 1, we're going to go from 0 and 1. So there'll be a term for 0, there'll be a term for 1. 1 minus 0 plus 1, 2. And it's the number of terms. We have 1, 2, like that. Okay. And then here we have n is equal to 3, and then finally n is equal to 4. And of course this can continue in general. So it looks to me that if you take this n value and you put that value over here, you're doing the same thing here. You're also taking the n value, putting it over here. So in a sense, if I know what the value of n is going to be, that gives me a very strong idea what the summation is going to evaluate to. And it's going to evaluate to 2 to the n minus 1. So I'm going to write...
Professor, if n is equals to 0,
n plus
equals
what?
to 1,
n plus what?
n is equals to 2 and 3. You have to
0,
3 and
1,
4.
2, 3.
So, right. Sorry. Okay. So what we have here is, so n is equal to 0, but this is 2 to the 1, n is equal to 1, 2 to the 2, n is equal to 2, 3. So it's going to be whatever, this is going to be 2 to the
Power n plus
power n plus 1
1.
minus 1. Now, is this a proof?
No.
No, but it's looking like it's probably true. So if we want to prove it to be true, not just guess, not just hope, because remember, even though the first 4 cases are true, it's possible the 5th case goes false. It's just coincidental, and that can happen a lot. Like it changes. So what we want to do is we want to be able to prove it. So to prove it, we're going to start using proof by induction. Proof by induction. And so the induction is going to require us to do 3 different things. The first thing is what we call the basis step. And the basis step. Now, of course, I should be a little bit more specific here. So since my value initially for n was 0, I should say that this is for n is greater than or equal to 0. And of course, we're talking about integer values. So it's going to be a sum, an arbitrarily high sum, because n does not, we don't have a limit, but we do have a lower limit. 0 is the first one. So typically when we go into induction, what we do is we take the value of the range of numbers at the lowest limit, and so the basis will be the case when n is equal to 0. And so what we want to do to show that this is good, we're going to try to make a proof, we have to first show that the basis, which is the value of the first value, makes this true. We want to show that this is true for the basis. And to do that, we're going to simply plug in n for 0. So therefore, we're going to have the summation as I goes from 0 to 0 of 2 to the I. That should equal to 2 to the n plus 1, which is 1 minus 1. Well, 2 to the 1 is just 2, minus 1 is just 1, and the summation of one term of 2 to the 0 is equal to 1. So this step right here, notice that I made a substitution for all the n values to show that when n is equal to 0, this means this, and it's true. That's it. Make sense? Okay, so now the important part of a proof by induction is we're going to... Very tall. It's all right. Not the worst thing. Can you see? Okay. Okay, so then I know that if I go lower, you're not going to see. I can figure that much out. So the next thing we're going to do in a proof by induction, we're going to do what we call the assumption. Or sometimes we call it the inductive assumption. We make an assumption. So our assumption is that this is in fact true. So we're going to say, we're going to assume, but we cannot use n because n is the general n, and it can be as high as we want. So we cannot assume that this is true, because if we assume it's true, we're assuming that what we're trying to prove is true. And you can't do that. That's an error. It's a logical error. Sometimes people say, it's a kid will say that. Why is it true? Because it is. They don't understand that that's not a really valid argument. It doesn't give you any evidence to support that. Okay? So when you say something is true, and you assume, let's start with the fact that it's true, and then go on from there, that's called begging the question. Begging the question. When you beg the question, you assume that what you're trying to prove is true, so it makes your proof completely useless. So the assumption will say, I'm going to take this n out, because n is the general n, it could be whatever we want it to be. I'm going to replace it with another variable. So in this case, I can say, let's assume that the summation as I goes from 0 to j. Why j? Why not? J, k, you name it, okay? Could be like that. and therefore 2 to the I power is going to equal to 2, and all I'm doing is really substituting j for n. So if this was from 0 to n and this is 0 to j, then because this was n goes to n plus 1, this is going to be j goes to j plus 1, right? Minus 1. So we'll assume that this is true, but we can't assume it for n, so we'll say let's allow j to go. First of all, we've already proved it for the value of n is equal to 0, so we'll say for j greater than 0, right? Because that's what's the smallest one there? 1, and less than n. And the reason we say less than n is because we can't beg the question. We can't assume that it's true for including n, because we're trying to prove it for n. So this assumption basically says, let's make an assumption that it's true for the next value, and all the values up to, but not including n. So that's the inductive assumption. So typically that's what you will do. You will basically make an assumption that your statement that you're trying to prove is true. You can exclude the basis value, like in this case 0, so that's why it's greater than 0, because it's already true for 0, so I don't have to worry about it. And you have to exclude the upper value, which is a general n value. Okay, so now that you made the assumption, what do you do next? So next what you do typically is you use the assumption and you try to use mathematical logic on the assumption, or argumentative logic. You can use word arguments, or you can use mathematical arguments. You make arguments to show that if the assumption holds for j, up to but not including n, you can logically produce a proof that it must also hold for n. So let's try it. So therefore, our assumption is fair game to use in the proof. So therefore, I can use j in any value as long as it's greater than 0, less than n. And typically what we do is we want to get as close as possible to n. So that means we maximize the value of j, which would make it. Okay. So now we have the proof step. So now we try to complete the proof. So therefore we will use inductive assumption for j equal to n minus 1. Okay? Because we can. So we maximize it. And so what's going to happen here is we take this inductive assumption and we replace j with n minus 1. So we're going to say the summation as I goes from 0 to n minus 1 of 2 to the I is going to equal to 2 to the power of j, but j is n minus 1 plus 1, so that would be what? 2 to the n minus 1. So and this is by the inductive assumption. Okay? Now, so what we have so far is that the sum from 0 to n minus 1 of 2 to the I is 2 to the n minus 1. But what I'm trying to prove is that this is equal to that. So I need to get this part right here to look closer to that part. Okay? So I need to have this match the left-hand side of that. And I need to have the right-hand side match that right there. So now I'm thinking to myself, what's the difference between the sum from 0 to n minus 1 and the sum from 0 to n? Well, basically it's one more term. Okay? One more term. And that's the term which is equal to n.
N is equals to plus 1.
So what can I write here to do that?
N equals to n plus 1.
Add 2 to the n on both sides.
Add a 2 to it.
Well, we can write, for example, that the summation as I goes from 0 to n of 2 to the I is equal to the summation as I goes from 0 to n minus 1 of 2 to the I. But that's not really true. So I have to do something what? What do I have to do? How do I make plus?
2 power n.
Because really, this is the same thing as this, except this has one fewer term.
2 power n.
So the term I'm missing is a term when I is equal to n. When I is equal to n, the term is
2 power n.
2 to the n. Or if you want to write it in summation notation, you can say plus the summation as I goes from n to n of 2 to the I. Does that make sense? So how many terms are here? N minus 0 plus 1. So it's n plus 1 terms. How many terms are here? This is going to be n, and this is 1. So it's the same number of terms. They're the same terms. So now we know by inductive assumption that the value of the first 0 to n minus 1 is going to be, this is actually equal to 2 to the n minus 1. How do I know that? By inductive assumption, so 2 to the n minus 1. And then I'm going to add to it this one term. And this one term is just equal to 2 to the n. So I have 2 to the n minus 1 plus 2 to the n. So what I have here is I have 2 to the n plus 2 to the n plus 1. But this is twice the same thing. So this is really equal to 2 times
Minus
2 to the n. There.
Which is
Minus
2 to the n.
Minus 1. So I have 2 to the n to the n, which is 2 times 2 to the n minus 1. But this is 2 to the 1 times 2 to the n. So that equals to 2 to the n plus 1 minus 1. And guess what? Now we have the right-hand side. Okay? And now over here, we have the left-hand side. So that completes the proof. Does that make sense? So this is an inductive proof. Now you might say to yourself, okay, I follow you, great, but how can that really be a proof? I mean, how can that really be a proof? I mean, you just made this huge assumption. What if I made an assumption and that assumption was wrong? Okay? And if I made an assumption was wrong, then I could show this, and this also, would that lead to the incorrect conclusion or the correct conclusion? So the answer is, it's correct. And the reason it's correct is something that I'm going to show you guys exactly how it works. Okay, so let's do another proof by induction, shall we? Okay, any questions about this? So the proof by induction is always going to be the same stuff. It's basis, assumption, and then the proof. And the proof has to basically put the glue together. And finally, get the inductive assumption to merge with what we're trying to prove. If you can't do it, then you're not proving it. Yes, what's your name?
Bhavya.
Bhavya. Spelled.
Bhavya.
Bhavya.
Yeah.
Okay, Bhavya.
In basis, we are assuming that n is equals to 0.
Well, the reason for that is because we are only trying to prove this is true for these values of n.
So indirectly, we are assuming in basis as well.
No.
For
In the
each-
basis, we do a direct plug-in.
Okay. So that it should be proof. So I can't put there.
So
n
this
equals
is
to
a
1.
proof of a single value. But n greater than or equal to 0 corresponds to an infinite set of integers, non-negative integers. So we have to prove it for an infinite set of integers, starting with 0, 1, 2, 3, 4, 5. So this proves it for 1.
This proves is only for 1 itself. Only
This
for
one
n
is for
equals to
1,
0.
but the assumption leading to the general is a proof for all. But I will, like I said, because you guys are graduate students or very, very motivated undergraduate students, so I will show you guys the motivation of why this is a valid proving technique rather than just saying, just do it. Because I'm going to show you why, but that's coming up.
So
Okay.
in basis, I can't take n is equals to 1 or 2 because that would be not equal to.
You can. Now, so the question is, that's actually a very good question that you have there, Bob. Okay, so the basis, because n is the smallest value, we chose that one because you got to start someplace. If we plugged in 0 and the statement was false, then the proof falls apart immediately because you have just disproven it. As soon as you plug in the lowest value into the, or any value into this statement and it's false, then it's not true. You have shown that it is a false assertion, a false assertion. Now, why do we choose 0? Because 0, if we can prove that it's true for 0, then all we have to do is prove that it's okay for 1 through positive infinity, right? So this shows us that it's not false, and this shows us that it's going to be assuming to be true for this range, and then we step it up to include the entire range, and this proof, union with this one, says that it's covering everything. Now, we could actually extend the basis and say, let's try it with n is equal to 1. If n is equal to 1, then what you would have is the summation would go as I goes from 0 to 1 of 2 to the I, and that should equal 2 to the power of 1 plus 1, 2 to the 2 minus 1, which we could also show is true. Because this is going to be 1 plus 2, which is 3, which is 4 minus 1, so 3 is equal to 3. So here's 3 is equal to 3. So this is a proof now for 0 and 1. And if I wanted to, I could basically say, okay, now you can only just worry about the numbers that are greater than 1, because I've already directly proved. This is a direct proof. The basis is a direct proof. But it's a direct proof of only one case, or in this instance, 2 cases. Now, the question is, do I need to do this? Do I need to do both of them? Can I do this one or that one? Well, I did this one because this one allows me to have 1 to infinity be contiguous. If I prove this one directly using the basis, and then I went here, then I still would have a question, well, what about 0? Whereas if I just did it for 0, and I included this one, then 1 was covered by the inductive assumption, and then the proof step included it. Now, you might find that this one is true, and maybe this one is false. If this one's false, then the statement is false. So you might discuss. So sometimes people like to do 2 basis steps just to make sure they're on the right track. But you are only required to be correct to do 1 value of the basis. In normal proofs, in normal inductive proofs. I mean, there's some special proofs that you may require a few of them because of the way the proof is formulated, but that's not that significant, not important. Okay, so let's take a look at another example of an inductive proof. So in this inductive proof, let's see, we're going to try to show another statement or another assertion. In this assertion, we're going to try to show that the function n factorial is less than n to the n for n an element of, what's z? Integers, and what's z plus? Positive integers. And I think I'm going to have to make a small adjustment. I'm going to make a small adjustment. I'm going to say n greater than 1 while n is an integer. So that means 2. And quite frankly, the reason I had to do that is because it would actually be false for 1. Because what's 1 factorial? What's 1 to the 1? So is 1 less than 1? No. But, so therefore the first number of interest for us is going to be which number? 2. And 2 would be 2 factorial. What's 2 factorial? 2 times 1. It's 2. And 2 to the 2 is 4. So 2 is less than 4. So it's true for the minimum value here, which is going to be 2. So our basis is going to use the lowest value available. So the basis is going to be for n equal to 2. And now we directly replace the values of n with the value of the n at 2. So we show here that 2 factorial is less than 2 to the 2, because that's the value of n. And that shows us that 2 is less than 4. And then we put a little check mark here, or say true. So that proves directly that the lowest value in our set is correct. So we have not been able to show that the statement is false. So now we're going to go to the assumption, the inductive assumption, and we're going to make an assumption. So again, in an assumption, we're going to replace n with another variable. We're going to call it j, because we're going to limit j with respect to n. N is the whole thing, everything. Okay, so we're going to say, we're going to assume that j factorial is less than j to the power of j. Now j, since we've already proved directly for 2, could be less than 2, which means that we're now looking at the range of 3, 2, anything up to but not including n. So it's going to be less than n. Okay? So now we have this assumption, and so now we're ready to make the proof step. And the proof step is we're going to try to take the assumption and move it towards this exact thing that we're trying to prove. Okay? So typically, again, we're going to do a very similar thing as we did last time, and that is we're going to go directly to the assumption, and we're going to take the assumption at its maximum value. And the maximum value for j is n minus 1. So we will plug in n minus 1 for every occurrence of j. And so that gives us n minus 1 factorial is less than n minus 1 to the power of n minus 1.
This is like smallest counterexample, right? Or is that?
Why is it counterexample?
Oh no, never mind. Yeah, it's induction. I learned induction, like doing +1, so it would be like k.
I can show you that way too.
Oh, okay. It's the same, like the same induction.
Same induction.
Okay.
But I can address what you're talking about. Okay, but let me finish this way.
No.
Okay. So so now what I have is n minus 1 factorial is less than n minus 1 to the n minus 1 power. So I want this to look like this. I want to transform it. So I can legally do anything with this that I can do with any other inequality in mathematics. If I want to multiply both pieces by 2, I can do it. Because if this is less than 2, then twice this is going to be less than twice that. I can do that. If I want to add 1 and add 1, I can do that because I'm doing the same thing. So therefore, if this is less than 1 more and 1 more, still going to keep it as less. Okay, so I'm free to do any type of legal mathematical, operation that I choose. That's going to make it easier for me. So when I'm looking over here and I'm looking over there, and I'm saying, how can I make this look more like that? See, this is different than the other example, because the other example we had a summation. So basically the assumption said I can sum n minus 1 terms, and I have to just add one more term. But here, I don't have a summation. I just have this. So the question is, I'm looking here, and I'm looking there, and I'm saying, how can I make it look more like that? Maybe I can't quite get it right. What can I do to both sides of this inequality and make them look more like the one on the left? And I think what I could do is I could multiply both sides by n. I'm going to multiply by n. Now, what is the value of n? I don't know. But I do know that the value of n is positive 3 or higher as an integer. Now that's important, because if the value of j could be negative, then multiplying it by n, if n could be negative, could be multiplying by negative, which would flip the inequality. You've got to be careful on that. But because I know that the value of n is greater than j and j is greater than 2, I know that n is greater than 2. It's positive. So therefore I'm going to multiply both by n, and I'm going to get n times n minus 1 factorial is less than n times n minus 1 to the n minus 1 power. Right? Now, one of my sides is now looking very, very good. Which side?
Left.
The left side looks very, very good because basically n minus 1 factorial is just going to be a product of n minus 1 down to 1. So when I put an n in front of it, that turns it into n factorial, which is exactly what I have in what I'm trying to do. So I have n factorial is less than n times n minus 1 to the n minus 1 power. So the left side matches perfectly, but the right side does not match perfectly. So again, so now I'm thinking to myself, what can I do? What can I do to show the right side, to switch the right side of the inequality to the one that I'm trying to prove? Well, so I look over here and I think about what the heck this thing is. Look at the right side. Right side is n to the nth power. That means you're going to multiply n by itself how many times?
N times.
So what I'm going to have is I'm going to have n factors of n. That's what I have, right? And what do I have on the right side here? On the right side I have an n, and then I have n minus 1, then I have n minus 1, dot, 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 and then I have n minus 1. So what I have is I have n minus 1 factors of n minus 1, and exactly 1 factor of n. Correct? So it's not the same thing, but what's the same is that the number of factors is the same. There's n factors here, and there's n factors here. And I also know that the value of n, so here I can put in parentheses n, what's the smallest value that n can be? 3. N is greater than or equal to 3. Is that true? So therefore, this value is at least 3 or higher. Positive. But this one is using values which are n minus 1. So that tells me that n minus 1 is at least greater than or equal to 2. Which is still positive. So if you look at it, let's take the smallest values possible. Let's assume, for the sake of argument, that n minus 1 is 2. If n minus 1 is 2, then I have 2 factors of n minus 1 and 1 factor of 3. And here I have 3 factors of 3. Which value is bigger? Left or right?
Right hand side.
Left.
Left.
Why? Because it's 3 times 3 times 3, and this is 3 times 2 times 2. That's the case. So remember, n is at least 3. n minus 1 is at least 2. So I took the smallest value. What happens if I increase this? So if n is 4, then n minus 1 is 3. So if n is 4, this is going to be 4. How many 4s? 4 times 4 times 4 times 4, and this is going to be 4 times 3 times 3 times 3, which is bigger?
Left.
The left. So now I can generalize that. I can say, well, if n is 3 or 4 or higher, basically what you're going to have is you're going to have one factor which will be the same as this one, a positive number, so that's always going to match. And then here you're going to have factors that are the same, but here you're going to have a positive number as one less. So that shows me that this will always be bigger than this, because these positive numbers here are always one higher, one higher, one higher. So the product will be greater. So from that observation, I could say this is less than n, the n power. And the reason for that is because each of these factors will be a positive number greater than each of these factors, positive number greater than each of these. Remember, so this is going to be n times, you can think of it as n to the n minus 1. So that's a match. And what we're saying here is, so there are n minus 1 factors of n minus 1, and here's n minus 1 factors of one higher, one positive number higher. At least 2, it could be 3, it could be 4, it could be 5. And of course, when n is large, these become really large numbers, but they're certainly bigger. And of course, this equals to n to the n power. So now we have this is less than this, it's less than this, which is equal to this. So now the proof is complete, because what I have is I have n factorial is less than this, which is that. So, and the reason I can do that is by what property of mathematics? It starts with TRA, transitive property. So if I have A is less than B, and B is less than C, so right, if I have A is less than B, B is less than C, then A is less than C.
I remember the factory n means 1 times 2 times 3 times 4 plus times n.
So
your
n,
left side is n times n.
so n factorial is going to be equal to, by definition, of n times n minus 1
Yes.
factorial.
Yes.
Okay, and then we have 0 factorial is equal to 1 by definition. 1 factorial, of course, is going to be 1. 2 factorial is going to be 2 times 1
Yes.
factorial. Okay, so that's sort of the general. So what was your comment?
Yeah, because your left side, the n factorial equal to n times 2 n times n.
So that's n power n. The right hand side is the n minus 1 factor.
I remember the first side, the left side.
So
is
I'm
the-
talking about this side.
Oh, okay.
Yeah. So basically I'm talking about this side. Yeah. This side, right, would be n times n minus 1 times n minus 2, all the way down to 2 times
Yes,
1.
yes.
Okay, now I get you. Okay. Yeah, so that part I didn't bother with too much, because that part, as soon as we multiplied both sides by n, we got that right away. But when we multiplied by n, we didn't get the right-hand side right away. So then we had to say, well, how can we still make this statement? And again, when you do the proof, you should give me a reason of what you're doing. Every time you do something, I can do this because n is at least this value, so it's going to, I can do this because it's transitive property. Something is less than something is less than something else. So this is, if it's less than this, and this is less than that, then this is less than that. Transitivity. Okay? All right, questions about that? So it's another proof by induction. Any questions? Make sense? Okay. I like when things make sense.
Professor,
Yes.
first we assume that n minus 1 is less than n minus 1 power of n minus 1. We just assume it. We did not.
Where? Here?
No, upward. Yeah. We just assume that statement, right?
No.
We did not.
No. So this is. So we didn't. So this is maximizing the assumption. But now what we did was we multiplied each of them. Since n is a positive number, we multiplied both sides of an inequality by a positive number. So this is just the multiplication property.
No, Professor. That statement, n minus 1 factorial is less than n minus 1.
Here?
Yeah.
This one here.
We just assume it. We did not prove it.
So this is maximizing the assumption. Because the assumption assumes for this, that means j could be up to, but not including n, so the biggest value of j is n minus 1. So we simply substitute for j, we substitute n minus 1, factorial, n minus 1 to n minus 1. So this is just maximizing the assumption. So this is the assumption specifically for the value where j is equal to n minus 1. Again, we cannot use n directly. We can't just say n minus 1 is equal to n, because that's begging the question. That's saying it's true because it's true. So the assumption cannot say it's true because it's true. The assumption you can assume up to, but you can't include the maximum value. Yeah.
Do you have to have a basis case?
Yes. You have to have a basis case.
So why couldn't you?
And I will show you, I will prove to you why you have to have a basis case later. Go ahead.
So my question would be, I guess that's what you're not sure, but why can't we assume that J is between is greater than 1 and less than n?
We could. We could. I mean, actually, so if you want to change this and say greater than 1, that's okay.
But then that would.
But somebody will say, well, you proved it directly for 2. Yeah, that's okay. The assumption you can assume something if you know one of them is true. It's still it's still a good assumption. Now, if you found that this is false and you put that into assumption, then you got a problem.
But 1 is not less than 1.
Huh?
We have already seen that 1 factorial is not less than 1 raised to 1.
But we're trying to prove that this is true for n greater than 1 integer. So 1 is excluded.
Yeah.
We didn't say this is true for all integers. We said it's true for integers 2 or higher. That's really what we're trying to prove. And that's what we proved. Would it be true for integers 2 and lower? Probably not.
We have to use the assumption, right?
Yeah. So, yeah.
I mean that we have to use that assumption to
You
prove.
should use so once you make the assumption, the proof step should take the assumption at its max value. Okay, so let me just, before I go on to contradiction, I want to go through and just look at induction. Some of you may have seen a slightly different approach to induction, but it's the same thing. So remember, we had to prove, the first proof I gave you is that we had the sum as I goes from 0 to n of 2 to the I is equal to what? 2 to the n plus 1 minus 1. So we want to prove it. So another approach to it, so I'll show you how to do it, and if you like that way, fine. If you're used to seeing something different, then you can see something a little bit different here. So in this case, we still need to do a basis step. And the basis step will be exactly the same as it was. Basis step is going to be n is equal to the lowest value possible, n is equal to 0. And so you have the summation as I goes from 0 to 0. You have to show it. I got to see this 0 here. You can't give me an n here. Of 2 to the I is equal to 2. If you want to be really explicit, you can say 0 plus 1 minus 1. Okay. And then from 0 to 0, it's only 0, so 2 to the 0 is going to be 1 is equal to 2 to the 1 is 2 minus 1 is 1, so you're fine. Okay? Now, another way of doing the assumption is we assume, now we'll call this a theorem. We're trying to prove this theorem, whether in fact it's a theorem. Or we can say whether our assumption, I don't want to use the word assumption, whether our assertion. So we're trying to prove this assertion, right? We can say assume assertion, which is what we're trying to prove, is correct for a value k. And of course, k can be at least 0, and then it goes into the positive integers. So in this case for k, and the assumption is that k actually is greater than 0, because 0 has been directly proved. So assume it's positive for, assume it's true for any integer k. Does that make sense? Any integer is positive. So now the proof step, what you need to do is you need to show that not only is it true for k, which can go arbitrarily high, including n, right? but also for the next value past arbitrarily high k, which is k plus 1. So what you want to do is you want to show that this will still be true for k plus 1. So you will write, let's do the summation as I equals from 0 to k plus 1 of 2 to the I. Okay? So you're trying to show that this is going to be true for k plus 1. So here's the value of k plus 1. Well, we know that the summation from 0 to k plus 1 is going to equal to the summation from 0, I is equal to 0 to k of 2 to the I, right? Plus the summation from k plus 1 to k plus 1 of 2 to the I. Does that make sense? Okay? So again, so this is a different approach, the same thing, and I'll show you why it's the same. So assume the assertion is correct for k, for any positive k, and now we have to show, for this type of induction proof, we have to show if it's true for any k under the assumption, then let's show that it's true for k plus 1. Since k is arbitrarily high, k plus 1 says it's generally true, always true. So therefore, that's why we're setting up from 0 to k plus 1. And therefore, we know, mathematically speaking, that if it's true for 0 to k plus 1, the summation from 0 to k plus 1 is 0 to k, and then just k plus 1. Right? And so therefore, the summation from 0 to k, but the summation from 0 to k is completely covered for by the assumption, which says it's correct for k. Which means that the summation from 0 to k of 2 to the I is going to be correct. So therefore, this will equal to what? 2 to the
K plus 1.
2 to the k plus 1 minus 1. Plus the summation from k plus 1 to k plus 1 of 2 to the I. But we know that's only one term where I is equal to k plus 1. So this is equal to 2 to the k plus 1. So when we assume the assertion is correct for k, that means that the assertion is true as I goes from 0 to k of 2 to the I. That's going to equal to 2 to the k plus 1 minus 1. If it's correct for k, for any k. So now we're going to have, this is going to equal to, this is going to be 2 times 2 to the k plus 1 minus 1, which is going to be 2 to the
K plus 2.
k plus 2 minus 1. So what we have here is that the assumption, we have I goes from 0 to k plus 1 of 2 to the I is equal to 2 to the k plus 2 minus 1. So this is true based on the assumption. Now, we want to show that this is true. Basically, this now, how do we show that it's true? So basically, this value of k plus 1 is just another value that can be substituted for k. So if you take k plus 1 and substitute for k, then the answer is going to be 2 to the k plus 1 plus 1. 2 to the k plus 2 minus 1, end of proof. Which way you like better? A or B? I mean, they both work. So why are they equivalent to each other? Well, they're equivalent to each other because in the first case, our j goes up to but not including n, but n minus 1 is arbitrarily high. So when you're trying to show that it still holds for n, you're going basically generally true. If you can go arbitrarily high and it's still true for the next one, then it's always true. If it's true for k and k is arbitrarily high, then k plus 1 makes it generally true. So you're really showing the same type of thing. And again, this does not make the argument why this is a valid proving technique. It just demonstrates the technique. We'll come back to that because I need you to sort of let this sink in a little bit, do a little homework with that, and then we'll show you why this is valid so you can be sure that what you're doing is actually going to be correct.
So either of the way we can use.
Say again?
The before way or this way, can we use any of them?
Yes, you can. As long as you're consistent. I don't want to see J's and K's together. Okay? By the way, before I get too carried away with stuff, I'm going to bring back again what I just erased. So the sum as I goes from 0 to n of 2 to the I is equal to 2 to the n plus 1 minus 1, right? And of course, this is not true, but it's true as long as n is greater than or equal to 0 and n is an integer, right? Correct? So this is true. How do we know it? We just proved it. Who said that? Who said we just proved it? I just want to know who gets an A automatically. See, who gets an A. You can leave the class now. You're done. That means he's listening to me and he's understanding. See, wish you said that. Okay, so this is true. Why is it true? We proved it. If you prove something and your proof is valid, it's true. Now, if you make a proof and you make a mistake in your proof, then somebody can say, well, that's not true. That step right there, not so good. All right, so now the question becomes, what happens if I have the sum as I goes from 0 to 10 of 2 to the I? So can I use that result right away? Well, sure, because now what's the value of n? N is 10. And based upon our result, this will be nothing more than 2 to the power of n plus 1, which is 11, minus 1. And of course, we know 2 to the 11th power is 2,048 minus 1, so this is going to equal to 2,047. Okay, so now let's suppose I have an example here. Let's suppose that, let's suppose m is an even integer. Okay, let's suppose m like Mary, is an even integer. I don't know why it's even, but okay, it's even. So now I want to compute the sum as I, even integer, and it's also greater than 2. Just to make sure I don't have any problems. Maybe it's okay if it's 2, but I'm going to make it greater than 2 just to be safe. If you can leave a small little area, that's okay. You can always look at that individually and say, okay, so also true. So I goes from 0. Let's say I want to have something like 2m minus 1 of 2 to the I. So now I want the answer right away for that one. Now, is this solution restricted to even integers or odd integers?
Restricted to even.
No.
To 4m minus 1.
This is only restricted to, this is true for all, I'm going to say non-negative integers. Non-negative because 0 is also included here, so non-negative integers. So therefore, if m is an even integer greater than 2, that means the smallest value m could be is?
0.
4. So the smallest value this could be is? 3. So this is, so does that comply with that? Yes, because the upper limit is 3. And 3 is certainly covered by 0 or higher. Right? Are you with me? Yes? So therefore, the value of this is going to follow this formula. So what we'll do is we'll do a substitution. This will be a substitution for n. So it's going to say it's going to be it's going to be equal to, sorry, don't need a summation here. It's going to equal to 2 to the power of 2m minus 1 plus 1 minus 1, which is going to be 2 to the 2m minus 1. Are you with me?
Yep.
Easy, right? So what I'm saying is, as long as the upper limit, even if the upper limit is an expression like some algebraic expression, as long as that value is going to be under the values that are restrictions for this, you can just substitute directly and get the value. Okay, now what if I have the summation? I want the summation as I goes from 10 to, let's say, m over 2 of 2 to the I. Okay, now let's say m is still an even integer greater than 2. Well, if it's an even integer greater than 2, it could be 4. That means the smallest m over 2 is going to be 2. So therefore, the upper limit is still good here, right? Because it's basically 0 or higher. However, the lower limit is not equal to 0. So therefore, you cannot simply substitute directly. So what we will say is, we'll say this is equal to the summation as I goes from 0 to m over 2 of 2 to the I, which includes 0 up to 9, and then 10 to m over 2. So I have to subtract the summation as I goes from 0 to 9 of 2 to the I. So now I can evaluate both of these summations. And so what I'm going to do is I'm going to have, let's do this one first. So this is going to be 2 to the power of, and this is covered nicely here. So that's going to be what? This is going to be m over 2 plus 1. M over 2 plus 1 minus 1 minus, open a parenthesis, and now we're going to have 2 to the I from 0 to 9. So now 9 is the value for this n, and this is going to be 2 to the 10th minus 1. Notice the parentheses are necessary, right? Because there are two terms here. So we have negative 1 minus a negative 1. Those two go to 0, right? Because you have negative 1 and you have 9 minus negative, that's plus 1. So this is going to equal to 2 to the m over 2 plus 1 minus 2 to the 10th, which happens to be 1024. Okay? So that's just kind of a fun math stuff. This is fun discrete math stuff. You just did discrete math, so it's like old hat to you. Like, oh yeah. Right? So we know. So that's how we can do it. Okay? Any questions about that? So if your lower limit is not 0, and it should be 0, then you can start at 0, but then you have to subtract. Because why do we do this? Because we know the result for this. And this minus that is that, so therefore this is the best way to do it. Quickest. Okay? So once you have a general solution that you proved is correct, you can plug directly into it and solve some problems. Okay, so let's do one more example, and the last example is going to be a proof by contradiction. And I kind of mentioned to you last time that proof by contradiction basically works like this. You're trying to prove that P is true, and in order to prove that P is true, you're saying, let's assume that P is false. And if P is false, then all these other things follow. Use those things that follow logically to show that that leads to a contradiction. It can't be. So therefore, your assumption that P is false can't be, and if P being false can't be, then P is true. So we're going to try to prove that the square root of 2 is not a rational number. Is not a rational number. Now, do you guys remember what a rational number is? A rational number is a number that can be expressed as a ratio of A over B, where A and B are integers. And of course, B cannot be equal to 0, but we know that, right? So a rational number is basically a ratio of two integers. So for example, a number like 1/3, is that rational? Yes. But its decimal value is 0.3, it goes on forever, right? So it's a non-terminating repeating number. How about 0.128? Is that rational?
No.
It's rational. It is rational. Give me an example of an irrational number. So we can use pi, we can use the number e, or we can use the number square root of 3. We know square root of 3 is 1.73, but it does not terminate, it does not repeat. So we can get infinitely close to radical 3. We know just where it is, but the closer we get to it, the more we realize that it's more to do. So we've got to keep drilling and magnifying and zooming in, zooming in, zooming in, zooming, but we know where it is. If you draw a number line, and here is 0, and here is 1, and here is 2, we know that square root of 3 is roughly in here. It's about 1.7 something or other. And we know that square root of 2 is about 1.4, it's going to be around here. But again, it's non-repeating, non-terminating. So actually we know that square root of 2 is not a rational number just because we're so smart. But we need to prove this thing that we know to learn a good technique. So in order to prove that radical 2, square root of 2, is not a rational number, meaning it cannot be expressed as the ratio of two numbers. Now think about this. What is 6/8 a rational number? Yes. But in fact, doesn't it also equal to 3/4? And isn't that also a rational number? Now how about if I do 1.5/2? Is that a rational number? No. It's not a rational. Now 1.5 divided by 2 is still equivalent numerically, but it's not a rational number. And the reason for that is because 1.5 is not an integer. So therefore, when we get to 3/4, we'll say this is in lowest terms. Now, would you agree that any rational number can be put in lowest terms?
Yes.
Well, any rational number. So if you have 80 here and then you have 34, I can put it into, what I need to do is I need to find out all the multiples of this, all the factors of this, and simplify it. Right? I know I can pull out a 2, divide a 2, that's going to give me 40/17. 17 is?
Prime number.
Prime number, so we know 17 is not a factor. So this is the lowest terms, right? This isn't, but this is. So every number which is rational may or may not be in lowest terms, but there's exactly one representation of that rational number in lowest terms. So, how to prove that square root of 2 is not a rational number? Well, first of all, we're going to, you think about it, let's do it directly. Directly, okay. Square root of 2 is not a rational number because I was taught in algebra class that it's not a rational number. Okay, that is not a proof. A really smart friend of mine told me it's not a rational number and he knows everything. Not a proof. Okay, so directly, where do you go with it directly? Come on, look at it. Look at it. It's not a rational number. That's called begging the question. It's not a proof. It doesn't look like a rational number. That's just that. All right, so not directly, okay. Now we try to do it by induction. But then induction, we're not looking at any number of infinite cases. We're looking at just this thing. So induction doesn't seem like the one, because induction is kind of like show that it's true for all these cases, starting here, going to infinity. That doesn't look like there's only one case. This is the one I want you to prove. So induction doesn't seem like a good idea. So maybe we should try contradiction. So contradiction, we're going to say, let's contradict what we're trying to prove. So let's assume radical 2 is rational. Because when rational, so we're going to make an assumption. If this assumption leads to a contradiction, then that means the assumption is false, and rational square root of 2 is rational false. Not rational means it's irrational. The negation of rational is irrational. Cannot be expressed as a ratio. So we are going to assume the opposite. Okay. So now what we're going to say, if that's the case, then square root of 2 is like any other rational number. It can be expressed as a ratio of A over B, where A and B are integers, right? B is not equal to 0, you get the idea. And because rational numbers can be expressed in lowest terms, I will say A and B are, A over B, I'll say A over B are in lowest terms. What does that mean? Cannot be simplified. That means they have no common factor other than 1. Other than 1. So, like 3 over 4, done. 40 over 17, done. There's no common factor other than 1. Lowest terms. Every rational number can be expressed as a ratio of integers in lowest terms. This is the ratio. So now, what I'm going to do is, since this is my assumption, I can flow whatever follows. This follows. If it's rational, then it's going to be one of these, like that. Because all rational numbers are like that. Then what I can do is I can use some mathematical things. So for example, what I can do is I can square both sides of the equation. So I'm going to do 2 is equal to A squared over B squared, right? How do I do that? I squared both sides of the equation. Why? Because I can. Because 2 equal things can be squared, and they're still going to be equal. Okay, so now I'm going to do something like this. I'm going to say 2 times B squared is equal to A squared. What do I do? Cross multiplication. Right? So I'm going to say, because A squared is equal to 2 times B squared, I'm going to say that means that A squared is even.
Yeah, right.
Now I'm going to make something very exciting. I'm going to say A squared is even, so that implies A squared is even. And if A squared is even, that implies, and maybe I do like implies like this, implies that A is even. If A squared is even, A is even. Now, I haven't said that before to you, like that, but I said it to you. And the way I said it to you is when we did our direct proof, we said if a number is odd, then when you square the number, it's odd. Remember that? So odd implies, so number odd implies number squared is odd. We proved it directly. Remember 2k plus 1? Okay. So this was our P, this was our Q. We proved it directly. But suppose I wanted to prove it indirectly. Then I would say if the number squared is not odd, then the number unsquared is not odd, even. A squared even implies a squared, an even not squared. So if a number squared is even, then the number not squared is also even. Well, since I proved odd number implies squared is also odd, I've also proved not odd squared, even, implies not odd, even, not squared. Does that make sense? Or am I losing you? Did I lose you?
It must be even.
A must be even.
Okay. So remember what we proved. So if, for example, if k is odd, then k squared is odd, right? We proved it. If a number is odd, then the squared numbers, I remember 3 squared is 9, 5 squared is 25, 49, 9, 81. We did all this stuff. But if you go to the contrapositive, if not k squared is odd, that means k squared is even, then k is not odd, k is even. So if a squared number is even, then the number itself is even. And so that's where I got this from. So this is just the different view of what we already proved. So a squared is even implies a is even. And if a is even, we know what that means. So we're going to say it just like that. Okay, so now what we're going to do is we can also solve this equation by solving for b squared. So if we solve for b squared, so if a is even, let's do it this way. So if a is even, that means a is equal to 2k, for k being some integer, right? So every place I have a, I can have 2k. So therefore, I can go back to here, and I can say 2 times b squared is equal to a squared, which is going to be 2k squared. So I get 2b squared is equal to 4k squared. And now I'm going to solve for b squared. So b squared dividing by 2 is equal to 2k squared. What is k? It's an integer. What is k squared? It's an integer. What is 2k squared? It's an even integer. That means that b squared, so this implies that b squared is even. And if b squared is even, that implies that b is even. So now I have determined that when I put square root of 2 into lowest terms of integers, I get the fact that a is an even number and b is an even number. Which means that they are not in lowest terms. Then I'm contradicting the fact that this can happen. This can't happen. I can't put into lowest terms. So therefore, since a is even and b is even, that shows that they have a factor in common, that shows I cannot put them into lowest terms. And if I can't put them into lowest terms, then that violates the fact that square root of 2 is rational. It is not rational. That contradicts the assumption. Therefore, if we contradict radical 2 is rational, that means radical 2 is not rational, and not rational is irrational. And not rational is irrational. Numbers that are not rational are irrational. That means they cannot be expressed as a ratio of integers. Get it? So that's contradiction. So contradictions, we'll do another example of contradiction. Because contradiction sneaks up on you. It's like, whoa, we're done. How did that happen? All right. I'll give you guys a little homework to play with. So expect that on Canvas. And I'll always give you like exact dates and stuff like that. So try to get those homeworks done. Remember, sometimes the homework can be tough. Sometimes it's going to be not so tough. Even if it's very tough, put a lot of individual effort into it so that when we go over it, it becomes clear to you and you have learned exactly how to solve these problems. Okay? See you guys next week.